Thank you, TheFamily, for inviting me. As I said, and we like challenging things and want to talk about the challenge of deep learning. We are in deep learning since basically I was working on this topic during my PhD for particle physics. So I was one of the few that was applying this to analyze really large amount of data, petabytes of data at CERN. And at the end of my PhD, I was thinking, what can I do with this algorithm? The idea is that it's good to have really powerful algorithm, but ultimately you need to have an application. And at the beginning, I thought about some topics, some things that were on the verge of disruption. And what of my thought is that if we want to change healthcare, we have actually to change also insurance. And insurance is something that nobody really likes. You don't like it because when you go, basically you have some problems, so you don't want to have any hassle. And the idea, if you want to really change insurance, you need also to change healthcare because the two are really connected. And what's good is that at the interface between technology, insurance, and healthcare, you can really bring some disruption. And this is what we are doing. And we have two aspects, two companies, one which is right now focused on developing the next generation of diagnosis devices and diagnosis technology that make in few seconds the same things that specialists are doing to reduce the cost and enable non-specialists to diagnose as well as specialists. And the other part is really specialized on providing insurance companies the best technology to reduce the hassle for you. And we are doing this with deep learning. And since I'm the first speaker today, the idea is to speak a bit about what is deep learning, what is the history of deep learning, and the next challenge. So everybody will say that artificial intelligence is on the verge of disruption and to be booming. So it's quite true, but not yet completely. There are quite a lot of challenge yet, and deep learning is a good option, maybe not the only single option, but one way to go and to make really quick progress in artificial intelligence. Yet there are a lot, but when I say a lot, it's a huge amount of challenges to be solved, and we are working on this and think that by working on the technology aspect, we also disrupt insurance healthcare for your good. So artificial intelligence is quite young. The idea is that it started in 1950, like 60 years ago, and it came with the first generation of technology, then what I call the desert traversal, because there were not a lot of technology appearing, performances was not really good, and a lot of disillusion appeared. And in 2006, someone actually coined deep learning, and we have seen for 10 years the emergence of deep learning that is now ready for production. And now that we are able to develop technology and applications that take advantage of this emergence of deep learning, we are what I call the industrialization era, and we expect a lot of the challenges to be solved. So the early days at 1950, the idea was Turing that created the Turing machine, and then the first version of what we call the neural network and the first step to go to deep learning emerged with several technologies. And what's funny is that in 1980, deep learning was already there, but it was completely not simple to use it. The power was not here, and it was really long to get the first result. It was invented by Yann Lequin, a French guy that is now the head of Facebook Research. 1955, random forest appeared, so if you are doing some data science, you pretty much use a lot of random forest, so it's pretty old. So data science is actually a really old topic, so not really sexy, it may seem, but because of the emergence of now GPUs and the next generation of technology, we came to new applications like IBM that was able to win at Jeopardy, and Google DeepMind that a few months ago managed to beat some of the best Go players. And now we are in this era, really interesting era, because everything is going to be industrialized. Like we were like farmers, we tried to do some things by our hand, and now the machine will appear that will make deep learning algorithm much faster to train, and you will have an emergence of a lot of application that will be powered by deep learning. And the idea is that we expect that time to send and to create this application will reduce, and this is one of the things that we are working on DreamQuark to be able to release in a few weeks rather than a few months an application that is as good as what human would do. I will start with shallow learning. So shallow learning was the old, before deep learning, the old machine learning. The idea was so the technology that we have, shallow learning, SVM, random forest, the old neural network we call perceptron. And the idea was that we were working with not a lot of layers, but really large layers. So a neural network is something like this. You have what we call units. So on the far left, you have the inputs, what you put, like pixel, like voice, like structured data. And on the far right, you have the prediction that you want to get, like a digit, a classification, a diagnosis. And the idea is that in between, you have a lot of layers. And in the old way, it was really complicated to have a large number of layers. So people make layers really large. And it was quite good. But all layers were kind of connected. So you have all the unit on the first layer were all connected to the unit on the next layer, and so on and so forth. And you have what we call a backpropagation algorithm that makes sure that when you compare the prediction to your result, you get actually a feedback loop that train your algorithm. And then you have some weight, so you initialize randomly or with some IDs. And then at the end, if you're good and you have well parameterized the external parameters that you have, you get some result and you expect good result. Also, you had unsupervised learning. The idea of unsupervised learning is that you don't have label, you don't know what to do, and you took your algorithm and you let your algorithm do the job for you. Quite complicated if you don't have the right data. And then came deep learning. And deep learning, we always say that deep learning is a revolution because we were able to put a lot of layers. Actually, it's a bit more complicated like that. The idea is that yet you have yes, you have a lot of layers, but what really changed things is that we put a lot of more creativity into designing this algorithm. The idea is that we remove this all connection, what we call right now dense layers, and we try to figure out what was the smartest way to have such an algorithm that work for voice, for example, for images, for video, for structured data, and you came up with different kind of architectures that are really good at each of these things. You take advantage of the symmetry in the data, and what we know now is that there are physical rules that are actually really well connected with the fact that deep learning is actually working. So you have numerous layers. You become much better at defining the metric success, much better understanding the hyperparameter, and automatize all this. And you have much more complex architectures, and these much more complex architectures give you, at the end, much more better and higher precision. And in deep learning, you can do basically all what you want, so that's really great because you have still supervised learning. So for example, if we speak about fraud, you have one guy that is frauding, you know he was frauding, you give this, and at the end you are trying to your algorithm to really be able to detect this guy. Then there is unsupervised learning. So the idea, you have no label, you have some images like dog, cats, you put these dogs, you put these cats, and you let the algorithm at the end categorize the cat and categorize the dogs. And if you have a large amount of data, it came to be really good at this. And finally, reinforcement learning. Reinforcement learning, like you have a mechanical arm, you want to train it to really good at, for example, catching a bulb. You don't want the bulb to be broken. You don't want to drop the bulb. So at the end, you try to make attempt and errors. And at the end, if you have a good strategy, you figure out how to take the bulb. And actually, it's already a bit more complicated like that because you can have like a continuum between supervised learning to reinforcement learning and unsupervised learning. And you can do, if you have this continuum, you can think about doing human level AI. And this is one of the things that we're working right now at DreamQuark. So deep learning algorithm is all these things. You try to automate the input transformation to be able to select the output better, to identify the best metric success for your program, discover the right set of parameters, which is quite difficult in is one of the greatest challenge right now in deep learning. You want to identify new cell pattern and the best pattern, the best cell and best connection pattern for your algorithm. You don't want your algorithm to do what we call hypertraining. Hypertraining is when you identify that one peculiar variable is actually generating all your outcome, but actually this specific variable is actually just a glitch, and you don't want this because at the end you want your algorithm to generalize if you give new data and even data that was not generated at the beginning. And the idea is that you work on building more efficient pattern, and you can do a lot of things until you did this, and came up at the end with algorithms that do the job in few hours, and which is great is that in 3 hours you can have results that are as good or better than the one that a large team of data scientists is doing, and we came up with such kind of things once we had all the other problem around data solved. At DreamQuark, we work on the algorithm design. We research an application to make them, at the end, integrate our commercial grade application. And on the side, during our spare time, we work on general purpose AI. So at DreamQuark, we have developed a lot of things, new architectures. We work really hard on basic principle understanding to be better at designing this algorithm, to work on to increase precision in image, voice, structured data, and time series. And we have several applications that have the best grade right now on the market with all the tests that companies that use it have actually done. So we work to improve the advance in NLP, work on medical imaging, work on emotional analytics or predict intent directly while the person is speaking. So a lot of things that is currently on the research topics. But the idea right now at DreamQuark is that we are releasing an infrastructure to train really efficiently this algorithm to be able to come to this industrialized way. And we have all these algorithms that are working to detect anomaly, to make unsupervised learning, pattern identification, classification, regression, predict, prescribe, detect emotion. And the idea now is to be able to connect all of this and we expect that by finding the way to connect all of this, we came up with actually general purpose AI. And in the meantime, it's used by some insurance company and healthcare professional. We have worked on the other company on automating diagnosis of several diseases. We started with Novartis with several eye diseases. There are 3 leading eye diseases: diabetic retinopathy, glaucoma, and finally DMLA. And we are working to provide these ophthalmologists. And we are already providing this for 2 of the 3 diseases, which are better than ophthalmologists, and we detect disease in less than 1 second right now. And finally, voice analytics solutions that are embedded into call centers. So this is one thing that we did on this disease. The idea is that you have some eye imaging. We work with several hospitals that bring us this imaging in India, in England, Germany, US. And at the end, you want 2 things: diagnose, be really able to diagnose really accurately this disease. But you don't want only to give a diagnosis or find out that there may be some risk. You want to identify where you need to put some needles and the treatment. And at the end, you get this spot, and it says, here are all the spots you have. These are due to hemorrhages, for example. And the general practitioner can send a report to ophthalmologist that will treat really quickly the patient. So there are, we will be maybe talk about the challenge we identify in deep learning lately. But there are some problems when you want to apply deep learning in a company like insurance. You need to figure out the problem and be really good and have a methodology to identify the success metric score, the scope of objective of your customer. Then there is data, and actually the data that they bring are generally not really good. They don't know necessarily really well the data, so you need to understand to help them and to put this methodology that you develop into a software in order that this software can be actually used even by non-professional and people that only know about insurance but not on the technical aspects. And finally, you need a lot of things around algorithms, so good algorithm. And to have a good algorithm, you need to have a good infrastructure. When you want to work in insurance, bank, or healthcare, it has to be secured, really secure, because you want to work with really sensitive data. And you have a lot of things to train individual to provide a way to industrialize all of this that we can talk later. This is done with thanks to a really good team that I have. They are amazing, really good, and awesome to work with them on the every day. You need to talk with them because they are really impressive in deep learning. Thank you very much.
Hi, nice presentation, thank you. I just have one question. You are working with insurance company, medical field. Do you have issues with the explainability of the algorithm that you are providing? How do you qualify the quality assurance? How do you ensure that the results are good and that they understand why the results are good, etc.?
Actually, this is one of the challenges of deep learning, is that when you have this neural network, you have like millions of parameters and sometimes even more, and it's completely useless to give them as the parameters because it has no meaning. So there are many things that you can give them. First, they have like use cases they already know that they use to assess the performances of the algorithm. In particular, in supervised learning, it's much more complicated in supervised learning because you let your algorithm identify things, and at the end, they say, okay, but why did you detect this? So we came to your specific problem. The idea is that you can have the architecture of your algorithm that is trained that give you some patterns, and you work to identify what are actually the most important trajectory in your algorithm, and with this you can compute which input, which combination of input is actually meaningful for this, and to have this for each of the individuals that you actually detect as something like leaving the insurance company, for example. And if you are really good at identifying this, and you came up with a really good precision, like there are precision, recall, sensitivities, specificity, and you give all of this, then they can understand what you are meaning. So we work a lot in order to simplify as much as possible this detection, and this is what we do for images. Like we detect the patterns, we don't tell them, okay, here is the diagnosis we did, here is the diagnosis we did, and here is why we did this diagnosis.
Okay, so hello, thank you for your presentation. My question is, what do you think about the frameworks, the AI open source programs? Do you rely on them? Do you plan on relying on them? Or do you think that it is better to have a homemade solution for everything?
I think you need this framework, and ultimately, you cannot. The idea is that when you work on deep learning, you want also to give things to the community because the community is giving to you. So this framework is a way to contributing, and the idea is that there are a lot of ideas that were emerging thanks to this framework, because you cannot work on everything. If you want to bring value, you need to bring more than what is currently existing, and this is a challenge of having a framework and having solutions that solve a specific problem and give, for example, better access to deep learning technology than a framework. So framework is good to develop all the environment, and it's much harder right now to dive into deep learning for anyone who has anyone who has ID but is not really good, for example, in programming or has no knowledge in deep learning, cannot really use the framework. And if you want to open up as much as possible deep learning to anyone, democratize deep learning, you need experts that take advantage of this framework and bring the framework contribution to the world by having much simpler solutions that are sometimes closed. So we rely on framework also. Yeah.
Hi, thank you for the invitation. So at Shift Technology, we do insurance fraud detection, which means that we sell to insurance companies an IT solution to help them detect fraud. And it's based on mathematical modeling, of course, because the outputs are results from algorithms. On big data, because I mean we have a lot of problems dealing with the data. And an important aspect of what we do is that we integrate a lot the know-how, the business know-how about insurance fraud into our models. First, some figures, just general figures about fraud, about the amount of insurance fraud. So it's the amount of insurance fraud is estimated at around 2.5 billion euros. So it means that it's quite important. This is for France, and this is for insurance in motor and home insurance. In healthcare, the estimations are less precise, but approximately the same. Which is when you compare it with, for example, the results of insurance companies, it's approximately the same. And also when you compare it with the taxes, we said that you can see that approximately insurance companies lose 4 times more money in fraud than they pay taxes. So it's usually a good argument for them when we sell the product. But today they detect very few. It was around 8%. So this means that there is, of course, a lot of things to do. But to really solve the problem, so the problem being saving more money, well, we need to deeply understand how to do it. And so in all insurance companies, there is a process, a claim handling process to handle claims. So a claim is, so for when you have, let's say, a motor accident, so you will do a claim to your insurance company. And so this is one claim, this is one file. And so for this file, you have first a claim handler, which deals with all type of claims. But then when there is some suspicion, they send them to the fraud handler that will look at it more in details to see, should we investigate more? And then at the end, so if there is more investigation, you can send somebody on the field to look for more information. And then at the end, question is, okay, now we have some elements. Should we suspect the client? And if yes, how should we do so? So this is really the work of the fraud handlers, and they make the money. But I mean, today this is very manual, but of course they have some challenges because there is a big volume of claims, of course, and the objective is to be the more productive for them. But the important thing is that since they make the money, and to make the money, it's never easy. So from the simplest case is you can simply intimidate a client. When you know that a client is doing a fraud, you can just say, sir, we won't pay you, this is a fraud. But sometimes it's much more difficult than that, and you have to go up to the trial. So this means that this involves a complex decision and action. And so it means that the goal is not to replace the process. The goal of an IT solution is really to slot into the process and to be an decision aiding tool for these fraud handlers. With, of course, all the challenges. First, challenges to process the data. So the classic V's of big data. But in insurance, mostly the main difficulty is the variety of the data, the complexity, not necessarily the volume, but more the complexity. And then the goals. This means that since the goal is to be an IT solution, in other words, the IT solution is only useful if it can aid the fraud handler to work. And he can work only if he understands the result. So this links back to a question. Because if we, let's say we had a solution that would detect that would exactly detect the frauds, if they don't know what to do with it, they won't make any money. So in the end, what we need is really a solution that says to the fraud handler, this is what you should do. So it means that, well, we give a score to order the claim by level of suspicion, but mostly the most important part is that we need to bring explanations and to visualize them. So I will come back to that. But so first, how do we do this? Because we need to do it automatically. So the first point is, what are the data? And I think what's important, so we mostly work with data from insurance companies and also some external data, typically about companies that we can gather. But the main aspect of the data is that it's structured and qualitative, which means that it's not numbers. So for example, we have on the data, we have claims. We have the date, the place, circumstances, given as categories. who was involved in the claim, the vehicles and stuff. We have the policy, the insurance policies, so the contract. So what are the covers, the options, everything, who are the declared drivers. We have information about the people, about companies. So all these information, as you can see, are, they're qualitative information. They relate more to conceptual compared to, for example, images or sound or other quantitative data. And this means that when you put all the data if you want to look at all the data, then you have a big mess because you don't really know, what to do with it. It's very also relational because you have many, for each claim you have the involved people that can be also involved in other claims, all the vehicles and stuff. And so this is the data that we need to deal with. There is also a first problem, is as Nicolas said previously, the data is very bad, it's very dirty, because all data from insurance companies are entered by hand, all the data is entered by hand, so it contains a lot of mistakes. And in particular, there is one central issue that we need to deal with, is that we need to know if a person was involved in several claims, because we want to understand what happened. But actually, we don't have a key to identify the person. We only have the personal information, such as first name, last name, let's say date of birth and address. But as the data is entered by hand, there are many mistakes. So we cannot do an exact match between the people. So we have this entity reconstruction problem or entity resolution problem, which is consists in linking these two, for example, Mathieu Dupont, that we know they are the same, but we need some intelligence to do it. And actually, this kind of problem, at first you can think it's only merging pairs, but it's not pairs because if you merge A with B and B with C, then you merge A with C. So there is some transitivity relation, and when you want to really work on this and have some efficient algorithm, there even is, it becomes quite hard because you need to deal with some partitions, and in the end you need very specific algorithms. We looked a lot in the literature, and actually it's really not developed. So it's a first, and yet it's a basic problem that we have because it's not even insurance fraud detection. It's just dealing with data from insurance companies in some sense. So we do it, and then we come back to the data, which is still very complicated in the sense that very relational. And on this, so we detect. We have two types of detections because it fits with their process. We have first detection where we try to focus on one person, and also it fits to two types of fraud. So this is for individual fraud. So one person, for example, that has let's say a claim, he doesn't have the cover to cover the claim. So what he does, he doesn't state the claim. He adds a new cover, and then states the claim by changing the date. So that now he's covered. But so it's a fraud because he was not covered at the time of the claim, so he's lying about the date. And then we detect collective fraud. So the case I gave maybe can be considered as a small fraud, let's say, but in collective fraud you can have very big cases that can involve a lot of bodily injuries and fake bodily injuries, people faking that they have like a neck pain or things like this, and they can earn a lot of money with this. Or sometimes it can involve some money laundering. We have some cases like this in Mexico, which is in the region of El Chapo. We have typical patterns of this collective fraud. So I won't enter into the details, but so just to explain the general principle of how we do it, if I just come back to what I said in the beginning, what we need is to have some explanations, and we cannot just look for cases that are fraud. So in some sense, we are not in a supervised setting where we would have like the past fraudulent cases and we could fit our algorithm. What we learn from is from the fraud handlers themselves. What we can only do is show them some results, and they can tell us if they understand. So this is what we do. So this is more like an active learning approach or reinforcement learning. And this is what we do. So we work with them and we present them cases, and they give us their feedback. So this is how the learning goes. But of course, the problem here is that because of the data, the data is very relational, and as we see, we don't want to analyze claim by claim. So as soon as we start saying, let's say we analyze like several claims, then the number of possibility becomes quite huge, and the number of models becomes quite huge. So all of our work is to design the models that will present cases to the fraud handlers the more efficiently, meaning that we cannot have too many mistakes. Let's say we present 100 examples and they're all fake, then we are shut down. So we cannot do this. So the whole challenge for us is to design these algorithms, and so we keep enhancing them through time. I have a quick demo I can show it maybe just after, I don't know the time, which is just to give you an example of such a network. But so just to conclude, just quickly about the functioning of the solution is so we work in a SaaS mode in the sense that we don't integrate our software to the IT systems of the insurance companies. They send us the data and we send back results. And sometimes in real time, sometimes like daily. But yeah, so this is how we work with them. Yeah, it was in South Asia, Malaysia, I think. I'm not sure. Well, it's just to show you that. So we end up with these networks that show people here that having claims. So there should be, I don't know. You should have information, but never mind. Having claims between them, and you can see sometimes that they're also having some family relationships, which means that they know each other. And so when you detect all this, many claims, in the end we found out that many cases were set up. I mean, is that they said they had a claim, but actually they did it on purpose, and then made a lot of money with it. So the bad thing of this is that we'll of course always detect once it starts to arrive, but when we detect it, then the fraud handler can work and avoid paying more for the fraudsters. Thank you.
Hi, thank you for your presentation. I'm wondering how ethic are going to be the big data you're going to gather from the people you're suspecting. Like, what are the kind of things you're going to gather to say if they are a suspect or not, and where is the code of conduct you're going to use for your organization?
This is a very good question because fraud handlers can be sometimes they have some very simple conclusions. Mostly outside of France, you always end up with these kind of things that you have some, let's say, communities that come up more in some frauds. So we don't use it at all. And for two reasons. First, because of course, let's say, three reasons. Sorry. The first one is because it's forbidden in France, and we don't want to do it. The second one is for ethic reasons, of course. And the third reason is that it's not because if you say like this is suspicious because I don't know they come from this community, it's not a reason itself. It doesn't help the fraud handler to investigate. So it's useless. It's also even you could say it's suspicious because it happened there in this area where we know, but this same thing. Otherwise, if you say this, then they will investigate all the claims there. So we don't use it. But sometimes when they give us the feedback, we are a bit disappointed because they could give something more than just it's suspicious because we know.
Hi, thanks for your presentation. Just for the same question, how do you come up with the bias that you said, like you use a score given by fraud analysts that might have a bias? How do you get rid of this bias in your analysis?
You mean the bias that they are more confident on some cases than others?
Yes.
At first we don't, because at first we need results. So we need them to work efficiently, because what happens is that we send the results. There's the first aspect, which is are our results good, in the sense our alerts are relevant. And this is good. But then the second question, more tricky, is are we helping them saving more money? Because if they don't save more money, even if our alerts are good, in the end, the director will say shift is not useful. So at first, and saving more money is not up to us, it's up to them. So at first we don't do it, and then we work closely with them through time and sometimes it's not that we teach them, but we when we propose a new case, each time there are the explanations, but also, I mean, when we make some changes into our model, we explain them not in mathematical terms, but we explain them why, and sometimes they learn. I mean, they understand like new cases, and so we evolve with them.
Hi, everybody. Hi. So for this special occasion, which is like the first occurrence of this meetup, I just wanted to go through a different pitch from my classical pitch, which is basically you need more data that has lots of value, and it's complicated because data is dirty, you need to clean it, and then you've got predictive technologies and artificial intelligence, and you can use it, and it's complicated, so you need some software like our software, the Haiku. So I won't do that speech. But would rather talk to you about a subject matter I fancy, which is the impact of artificial intelligence on our lives as human beings. And so what's the relationship of a human with the machine? So my actual starting point is far away, like when I was a kid trying to make computer works, which works anyway. And so when I was a kid, I was going to the public library, and so my way of reading books was basically to choose one author, and when I was happy with the first book, I would read the complete list of books from that specific author. And so that's how I basically read all Asimov when I was 6. And so, oh, okay. When I was 6, I've got my computer trying to help me with from assistant to set up a new keyboard, which is not so helpful. Okay, oh, it works. And so the things that I really liked about Asimov is that he was building like a complex world with different narratives through different books, possibly not completely consistent with one another, but with this big story and universe about robots. And so there was those 3 laws of robotics, making everything consistent, and that he would use in order to see what would be the limits of robots programming and the moral laws for robots, which would basically be that they should not harm a human, do what a human being would say, and not try to commit suicide, basically. And so I would, makes sense. And also I really like this particular character, which is Daniel. We basically was like a robot, but who was looking like a human to the point that over the course of several hundred years, he actually more or less started to think like a human. So yeah, obviously lots of narrative and possible stories around that. And so because of that, I actually spent a great deal of my teenage years actually wondering how this would actually become true, meaning robots and humans actually talking to one another, and EA and so on. But the bad side of things is actually that when I was young, it was, and a teenager, it was actually the winter of EA, meaning nothing was really working in terms of artificial intelligence. AI, sorry. I keep saying EA in English, which is completely stupid. So yeah. But that all the French speakers in the room, which is, I guess, almost everybody, can understand. But so yeah, so basically nothing was working in terms of AI. And so what drastically changed in the last, I don't know, 5 or 6 years is that suddenly many things actually started to work in artificial intelligence. I don't know if actually anyone understands actually why it started to work, like right now in this moment. It is just because of computer, new techniques, technology, algorithms. Nobody knows, but things started to work. And so today, we start having actual self-driving cars, which is amazing to me. Meaning I can't actually drive a car. So my own expectation is that I would keep staying that way, not being able to drive a car for about 20 years, but right now I'm pretty sure that in 10 years I will be able to go to California and just buy an automated car. But the thing to understand is that for any of those systems, like an automated cars, you've got many artificial intelligence subsystems in order to be able to determine just the velocity of the car and what's in the road or the weather and so on. each of those needing some specific predictive models, and then you need to be able to connect all those things together and make them work in a safe way. And the reality is that like 10 years from now, each of these boxes is probably a piece of software which was almost impossible to develop like 10 years or 15 years ago unless you were the NASA or an organization about of the same size, like NASA or Microsoft. And so the same way you've got, which is something which is pretty frightening to me, is that you start to having robots, artificial intelligence doing some arts. And so, well, basically because it's artificial intelligence and you can easily apply it on the internet, you end up having cats arts. It makes sense. But here again, it's pretty interesting to start to understand how it actually works, meaning you have like an artificial intelligence that captures by learning through different images, a particular style, by looking at how colors are actually combined together and how shapes are actually combined together at different scale within a particular image, capturing this way the style of a particular painter. There is a similar story with writing. Like, I don't know if you noticed, but like I think it's 5 months ago, there was a piece of a very short movie, like 11 minutes, which was actually written by a piece of software automatically, then shot by a human being. And so this particular movie is pretty strange, meaning it was actually trained using lots of sci-fi books. So I think that the next scene is actually the guy here actually taking an eye from a bowl and eating the eye, which does not make sense. But the movie itself is watchable, meaning I've seen worse movies written by human beings. And that's very scary, meaning I do fancy some writing, and that's very scary for me. But so you also have like artificial farming with actual robots helping farmers do their stuff. You've got lots of AI applied to medicine with like things we actually work on, like automating the analysis of brain waves. So today, a doctor specialized in brain waves and EEG stuff, like a neurosurgeon and alike, they do need real time in order to actually read brainwave analysis. Meaning if you capture 1 hour of data, they would typically need 1 hour just to analyze the data. And so the next generation of devices will basically capture days of data from patients using connected devices. And so you do need computers just to make the work of doctors, just because you don't have enough doctors in order to read the data that will be generated by the next generation of devices. But so, obviously, again, these systems that are able to do the stuff that someone that was trained for 7 to 10 years to actually accomplish the task. So these systems are incredibly complex, meaning you need several man-years of research, then several dozen of man-years of implementation in order to actually accomplish this. So, an interesting question is, this will actually apply to the good old corporate world, where in most situations, we don't have that many fancy devices and life-threatening situations, in fact. So, the thing with data in general is that, like in the last 20, 30 years, you obviously had more data inside companies, and then a first generation of management consultant using Excel, then dedicated data teams that were working on data, providing more reports, and so on, and so on, and so on. That was like the first generation of apps. I think that a big trend today is to have a kind of a new generation of stuff where you got previously this, in an enterprise you basically have a business process apps where you try to capture a business process automatically through an app. It basically replaces a folder, like a physical folder online, and you've got reporting apps just to tell you what happens inside your company, like graphs and charts. And so most of the interesting applications I saw in the enterprise are applications that, such as the one from Shift Technologies, application where you try to combine a business process and lots of data, but so much data that actually people cannot actually analyze it on their own. So they do need some intelligence that would suggest them where to go, where to look for, and so on. And so obviously overall, the way of the way of making this possible is by getting this new artificial intelligence technology, which is just an evolution of what was done before. So nothing new, in fact. And so this is the way you've got now people that try to automate marketing campaign, or people that try to automate logistics processes by automating the forecast of demand. But back to the interesting question, an interesting ethical question is the fact that you got on the left an analyst. So actually it's someone from my team. It's our data analyst. And so the job of an analyst over the last 10 years was basically getting more interesting inside most of the companies. Just because you've got more data, hence a need for analysts that do some data analysis. And so a question is, I think that over the next few years, there is this trend of having more automated decision making, where the robot over the time would kind of take the place of the analyst. And so the question is, what is the future of this job, analyst? Do you just stay on your bench and watch a robot taking decisions that was actually programmed by a data scientist who is better paid than you? That's the actual question. And so obviously I was talking before about Daniel, the robot, but actually Daniel from Asimov is just the next generation of all fears we have all. That started with Frankenstein and even before with the golem. Nothing new under the sun. So what are the actual risks behind artificial intelligence? Well, one risk is obviously that it could be controlled by the few. And it does make sense because the companies that won the war 20 years ago about content and websites were basically companies that were able to leverage their technology to release their website really, really fast. Well, they were good at many, many things, but one thing they were all good at was just releasing their fucking website. Yeah, that's true, meaning they could just update their website every day. And most of the other companies could not do that. And so the question is, will the same company, just because they are able to get data and put artificial intelligence in motion and in production, just because they have this capacity today, would they be the winner of the war 5 years from now? And so another question is, well, question of the position of the human being himself. Meaning, let me elaborate on that. Imagine a company, so this can actually happen, meaning it does actually happen sometimes. You can imagine a company where you've got an artificial intelligence, like a corporate artificial intelligence, that would just say to some of the employees that they should call a specific customer. Then when you read to write an email, it would generate the body of the email, but possibly ask an employee to actually write a joke inside the email, because the artificial intelligence is pretty good at targeting, but maybe not so good at jokes. So it does need the need of a specific employee to do that. And then it would just put actual meetings inside the Outlook calendar or Google Calendar automatically, which is very annoying. I don't like at all people putting Google Calendar invites directly in my calendar. But, so you could have just a corporate artificial intelligence doing that. And so the actual risk is that salespeople, if managed this way, just would have no hubris, meaning they would have no actual reason to sell just because it's not funny anymore, which is a big risk, actually. Another interesting situation, and actually also related to the insurance industry, is coming from this particular paper. You must have read it because it was like on Hacker News for about, well, almost 8 hours, 5 months from now. 5 months ago. Oh, sorry. Yeah, I'm very predictive. And so it's the question of the morality of the automated car. And so basically here the question is, you've got an automated car, there are 10 people crossing the road. Should it just go on the right to hurt one guy standing on the side and just kill him instead of killing 10 people? Good question. First variation, if there is just one guy, but you would hit a wall and kill the driver, possibly. What do you do? It's not obvious, actually, because if you do kill the driver all the time, it might be that the driver would rather shut down the automatic driving mode. I would do that, even if I can't drive. And so, yeah, and what happens if you've got like 10 people crossing the road? That's not obvious. And so, overall, the question around that, is like, today, when you're building these new data applications, you obviously have concerns about security that you hear all the time. Is my data secure? You've got concerns about privacy that we all know them very well, unfortunately. And so I guess that in the future there will be a question about legitimacy, meaning it's not the right word. I can't find the actual right word for this, but it's the fact that when the application, the decision made by the application can be derived from the actual will of a human being, meaning you can understand why, as a human, someone would have taken this decision, which is a particular characteristic of application you would want to keep, just to avoid that people that would be subject to the decision of the machine would just start revolting. Then, because I think I'm quite out of time, so I'll switch next to the next slides, where basically a big question is, I think, in order to make this application work in the corporate world, where you don't have these life-threatening situations, it's what is the actual role of the user and the machine. And so, obviously here, the question is the kind of patterns of interaction between the human and the machine. And so depending on the application, you can imagine different patterns, and questions like applying and designing those patterns so that the human being has enough freedom in order to be happy to use actually the artificial intelligence. And so my takeaway is that because of that, if you've got a children which is more than 10 years old, it could be a good idea to try to turn him or her into an AI experience designer, which would be like possibly a very trendy job 5 or 10 years from now, almost as much as a data scientist or a UX designer. And that was actually my takeaway.
When you look at the kind of jobs that are being automated, so when you look at the analysts being replaced gradually, to those in the audience and those watching later, what's a good sign that your job is one of those jobs that might become very easy, if not replaced, in the next few years?
I think that the fact that you are not happy about your job is a good sign of it being replaced. And so specifically if you are doing lots of repeatable things over data that is over data, that could be the case. Well, meaning, let's take a specific example. Today you've got analysts inside corporations that would go into application A, let's say Google Analytics or Facebook ads or whatever, then application B, download some aggregates over a time span into those two applications and copy-paste the result into Excel and then try to reshape the data and then try to make a PowerPoint presentation out of it. And they would do that almost every day. You could imagine this kind of job being automated a few years from now, obviously. And so, yeah, a good sign would be repetition and the fact that you don't actually leverage all the data you can just because your eye would not be able to do it.
Okay. And if there's too many cool tools doing most of your job, is that a sure sign that you're next?
Yep.
Okay. Thank you very much. So maybe doing jokes all the day would be a good job.
Yes.
Thank you.
Que l'enfant